Great. So for those of you not born when LRO launched, a little bit of background. Mini-RF is a two-band, two-resolution imaging SAR. We have capability of taking data in both S-band, which is 12.6 centimeters, and X-band, which is 4.2. Typically, we use a zoom resolution, which is 30 meters. Most of the data I'll show you today is that. We also had a baseline resolution to match the resolution of the instrument that flew on the Indian Chandrayaan-1. First, the bad news. I had to put this at the beginning or the end. I thought I want to finish on a happy note, so I'll get this in early. On December 26, when Mini-RF suffered an anomaly, essentially the transmitter stopped failing. There were a number of possibilities, including component failure or a broken connection. On the off chance it was a broken connection, we tried a test where we heated up the instrument because it could have closed the connection. And sadly, it didn't work, and no current plans to operate the transmitter again. That said, we're not dead yet. The receiver is still working nominally. We're looking at future science experiments, including possibly bistatic, as I'll talk about a little later, and ionospheric measurements for the moon. We collected, in total, we had 3 different phases to operations. We had the commissioning phase, where LRO was in the elliptical orbit, and then the ESMD 12-month mission, where we took about 1,400 passes, and during the SMD phase that began in September of last year, we took about 400 for a total of about 2,100. So this was the coverage we got during the first year of ops, and then we were concentrating on the Northern Hemisphere coverage, so we filled that in quite nicely during the SMD phase. Well, there is a delay. Okay, and then here we have the North Pole coverage from the ESMD phase, and we were quite successful in expanding that. These aren't very pretty, so I now want to, oh no, I'm going to show you real data in a minute. So, with regards to coverage, we got about 2/3 of the total lunar surface, slightly more of the far side than the near side, and we got between 98 and 99% of both polar regions. There we go, real data. So here we have this is a circular polarization ratio image showing within 20 degrees of the North Pole. And I want to zoom in on, this is one of the things that we were successful in doing during the S&D phase is, I should point out that because we're a SAR that points out to SARs point out to the side, you would typically get a gap around the pole because you don't look straight down. And this gap would be about 1.5 degrees in latitude. Fortunately, the moon has a funky gravity field, so the orbit wobbles slightly. And we took advantage of that wobble. And these are some passes of data that we took very close to the North Pole. So the North Pole is in here. This is Peary crater, about 78 kilometers in diameter. This is Whipple. So the nice thing about this is we covered some of our interesting craters with regards to the potential for ice deposits occur here within the floor of Peary, and we managed to get those. Also, we were actually taking X-band data. Sorry, the previous mosaic was S-band. We were starting an X-band campaign when we failed here. So this is Peary. So we got about 60% of the North Polar region in X-band. Again, including, here we have the craters in both S and X-band. And these craters here have an interesting radar signature where you see enhanced CPR only inside the craters, which is at least consistent with the idea of a regolith ice mixture. Although one of the things we still want to do is do some bistatic experiments. This beta angle is the angle between the transmitted beam, essentially, and the receiver beam. So when you're using the same antenna to both transmit and receive, you're naturally taking data at what's called beta 0. The physics dictates that you could have high CPR both from a rocky surface and from water ice at beta 0, but they would behave very differently at different beta angles. So one of the things we can do with an active receiver is by using Arecibo as a transmitter, we can take some data at beta angles out here and try and see whether we still see high CPR or not inside these craters. Calibration is progressing well with the instrument. Any of you who use some of the early data, you may have experienced a sort of a gradient that you see in range in the circular polarization ratio data. We know why it does this. We've managed to take some good calibration data, again, using Arecibo as the transmitter, so it's a well-calibrated source. And we're progressing. This is an initial version of the calibration where you can see that the gradient is much reduced. This is allowing us to try and be cleverer with the data. This is an M-delta decomposition where we use a hybrid polarization architecture where we transmit a circular polarized signal and we receive linear polarization and the phase information. This allows us to generate the 4 Stokes parameters for the return signal, and from that we can fully characterize, or much better characterize, the radar backscatter nature of the lunar surface. We can use the Stokes parameters then to derive what are called daughter products, such as degree of polarization and degree of circularity, and we put these in an RGB image. This is an example here, where the different colors actually tell us more about the nature of what happened to the radar, whether we had a double bounce, a single bounce, or volume scattering. And one of the things we're finding is we see a lot of information can be gleaned from the ejector blankets around craters. One of the goals of LRO was to image the 50 constellation sites. We made this a priority during the first year. We imaged about 32 of those sites directly. This is one of them inside. This is the melt pond inside King Crater. It's actually quite nice because you can see the melt has actually flowed up onto the rim of the crater, and in fact the topographic high is about here, so the flow has actually gone over that and down the other side. And we imaged actually 49, in fact, of the 50 within 40 kilometers. Just some highlights that the science team are doing. One is measuring, this is an example of measuring detected buried flows. This is the crater Gerasimovich D. This is an LROC WAC image. You can see in the CPR and that it's very clear that this melt flow, or this flow, it's very smooth, you can see in the optical data, and yet it shows up as high CPR, which typically would be rough. So one scenario is we're actually looking at a buried flow, where you've got a thin layer of regolith on top of this rough flow underneath. We now, for those of you wanting to, because we have got 2/3 of the lunar surface, you can do more than just look at single images. You can try and make mosaics of your regions of interest. And what you can see here, where you have 2 neighboring strips, if you're just relying on the SPICE information for the spacecraft, you can get uncertainties, which is a nice word for this. But we now have the software tools available to pick match points, and you can produce nice controlled mosaics, which is particularly important if you then want to correlate with other data sets such as LROC or Diviner. At the South Pole, we took some of the first data of the floor of Shackleton crater. We have good coverage of the South Pole, and now you can see how the floor of the crater is offset because it's a time delay. So something that comes from deeper with the initial processing just looks like it came from further away. But now that we have the excellent LROC topography and also, the Lonar topography and the excellent LROC topography, it's all topography all the time, you can now actually do a pixel for pixel compensation for the topography, and you can actually bring these back into the floors of the craters back into the middle where they belong. Again, it's an important thing to be able to do if you want to do multi-data sets comparisons. Here we have an example of impact melt. This is an impact melt flow inside Tycho crater. Here we have the terminus of the flow, and what's interesting is you see a change in brightness here, which possibly indicates a change in morphology from, say, this is brighter, so it represents a rougher surface. You could have an RR to Pahoehoe, for example, transition here, and what's nice is if you put the Lonar track through, you can see that where you see this change in CPR does correspond to a change in slope, again possibly supporting that you're seeing a change in emplacement velocity, which could cause a change in surface morphology. So one of our team members now, we have 2 of the regions of the moon that we potentially have the best coverage. One is Oriental and the other is South Pole Aitken Basin, fortuitously. And this just shows you sort of the depth of coverage that we do have for those of you wanting to do of regional studies. So actually, I could pretend that I'd actually thought this through really cleverly and that I'd put this up because it was the anniversary, but that would be a lie. So the slide on the left is a mini RF image where you can actually see the LEM, and this is a nice LROC image. And the reason for showing this is from an exploration sense. One of the things we're looking at is how you would use the data to help you to determine whether landing sites are good landing sites. And you'll notice here how the area around West Crater is very bright in the radar, indicating that which tells you immediately that you have a high number of blocks. If only I cared what you thought. And one of the things we're doing, we want to go back, if those of you who've listened to the Apollo 11 transcript from them landing, is when Buzz starts to say, oh, yeah, we're getting low on fuel. And they do see lots of boulders, which is when Armstrong took manual control and moved it. And we're trying to investigate, in fact, is this a boulder field that isn't immediately obvious in the WAC data, and try and use actual examples to learn how you would use the radar data to help pick good landing sites. So last two slides just showing, again, nice sinusoidal projection, just showing the amount of data. This is what 2/3 surface coverage looks like if you pick a good map projection. And then finally, we're very excited by this M-delta decomposition. We think this will tell you more about the surface geology. This is a very new, we're just starting to produce this, and we've just finished our first sort of global map of this product, and we're delving into it to use for science and exploration. Thank you.
Questions for Ben? Irene. Here comes the microphone.
Thank you. So, when is the absolutely corrected, topography corrected data going to be available to the rest of the community?
Well, that's beyond the scope of the team. What we can do is show you how to do it.
Fair enough.
We have the tools in place to show you, how you would do that yourself to make your own topographically controlled mosaics.
Okay. And the data is where?
All the data is in the PDS.
It is? Okay, great. Thank you.
Other questions? Wait for it. Okay, all right.